Hi, this video relates to 15C, the binomial theorem. So this is going to relate back to our combinatorics where we looked at combinations or NCR. So let's read the notes first. The pattern of numbers that are formed from Pascal's triangle are identical to the numbers that arise when counting unordered selections of R from an n member set, and that was what we used for combinations. So if you remember back to our combinatorics, NCR was the same as writing n and r like this in brackets. We didn't do that a lot, but that's the same thing. And NCR is also written as n factorial on r factorial n minus r factorial. So that's something that we should know by now. Over here on the left, it shows us what the binomial expansion expressed in sigma notation is. And just note that, but we're going to have a look at that in a little bit more detail. So we looked previously at expanding 1 plus x to the n in 15a is what we looked at. And here it says, and that little symbol there, which you may or may not have come across before, it's another Greek letter in the Greek alphabet, and its name is sigma. But in maths, all it means is to sum something or to add something up. So although this looks pretty messy here, we're just saying here, sum up from 0 to n, NCRs of x to the power of k. Now, that won't make a heck of a lot of sense yet, but what I want to show you is that the NCRs, if placed in a Pascal triangle format, are going to give us those values based on what the n is and what the r is. So what I've done just over here to the side in orange is placed n equals 0. I've just done it to n equals 3, but this can continue going on, where n was our row number that we had for Pascal's triangle. So if I have a look at placing in my numbers into Pascal's triangle, where that n at the top relates to this n here, C0, because our first r is always going to be 0. For n equals 1, we're going to have 1C0, 1C1. You can see a pattern here. For the second row, 2C0, 2C1, 2C2, etc. Now, if you were to pop those into your calculator, you're going to get 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So our NCRs give us the values of the Pascal's triangle. So that's what we're going to do in this section, is instead of actually calculating Pascal's triangle by drawing it from scratch, we can work out what the coefficient is at any point within that triangle based on its n value and its position value. So it's a heck of a lot easier to work out our coefficients. So what we've got here, and this looks very scary, but it's not, is our expansion of x plus y to the power of n in terms of our coefficients that are Pascal's triangle, but it's generalized. So we're basically saying that our power n is our value at the top, c, and we always start at 0, and we're going all the way up till we get to ncn. So our coefficients are written in there, up to ncn. And we always start with our x at its highest value on the left. So x to the n is up here. So therefore y to the n is at the other end. The x is decreasing. So our next term there would be n minus 1. And our y's are going to be increasing. So here it's y to the 0, y squared, etc. So that's a generic expansion of x plus y to the power of n. Now we can have a look at particular values of NCR. And what you want to remember in Pascal's triangle, that each row of Pascal's triangle is symmetrical, such that for the numbers n, where r 0 up to n, NCR equals NCN minus r. Other properties that are also important, such as the first and the last numbers are always 1. So NC0 and NCN are 1. So let's go back to this one here, NCR equals n minus r. And that's just basically saying that this one here, so if this is NCR, that's going to be the same as 3C 3 minus 0, which is 3C3, which is the other end. So 3C1 is going to be the same as 3C1, 3 minus 1, which is 2. So it's just telling us that at either end, in identical spots from the ends, they're going to have the same coefficient. And this one we just said was saying that those ones at the end are equal. And the second and the second last numbers are equal to n. So NC1 is equal to NCn minus 1, which is n. So that's saying here that 3C1 is 3, and our power is going to be 3 because it's the third row. And 3CN minus 1, in this case, 3C2, sorry, would also be 3. You can see those two 3's there. So they're just some things to take a note of for this topic. Okay, the k plus 1th term of the general binomial expression, which is the same as what we've got up here, okay? And we've got this expansion. So this is just basically expanding a plus b to the n, which is the same as x plus y to the n, just another way of writing it. NC0 is the same as n0 in our brackets. Instead of x to the n, we've got a to the n, but otherwise that expansion is just a different version of this one here. But what we're saying here is that k plus 1 term, or term k plus 1, is equal to nck a n minus k b to the power of k in this expansion here. Okay, and a version of this expansion is given on our HSC formula sheet. So I'll pop over and show you that. So on our very last page under combinatorics, they've got the expansion of x plus a to the power of n written slightly different. So they've written it in terms of NC1 is written with the brackets in there. They haven't popped NC0 in because that's going to be 1, and they haven't popped NCN in because that's going to be 1 as well. But other than that, it shows you this generic form here, that any expansion in that is going to give us a term of NCR x to the n minus r a to the r. That basically shows us this rule here within that expansion, which is really handy. Okay, so we're now going to use the binomial theorem to calculate the coefficient of x to the power of 8 in this expansion. So x to the power of 8 in 1 plus x to the 12, we'd be expanding that like we've got over here with a 1 where the a is and an x where the b is. So we'd be looking for x to the 8 to be along here somewhere, and our coefficient would be 12C8, which would give us a coefficient of 495. So the term of x to the 3 y to the 4 in x plus y to 7. This one's looking for not just the coefficient but the term. So if we move along in the same way where we're studying for the highest power of this first position, here in the formula it's a and that's moving down. We've got y and x. So x has started at 7 and it's moved down to 3, and y started at 0 and gone up to 4. So we're looking at 7C4, x3, y4. So you're just going to pop that 7C4 into your calculator and you're going to end up with 35, x to the 3, y to the 4. Okay, so this next one's a little bit harder. So it's asking us to find the coefficient of a5b5 in 2a minus 3b all to the power of 10. So we can do that, and then it wants it factored into primes. So let's not worry about the factored into primes part first. Let's just look at the coefficient of a to the 5 and b to the 5. So if we were going to be expanding this to the power of 10, we're looking for the coefficient of a5b5, we'd be looking for 10c5, but we'd have 2a to the 5, and we'd have minus 3b to the 5. So I'm just to start with ignoring the factored into prime speed. I'm just going to go as we otherwise would proceed. So 10c5 is 252. we're going 2 to the 5a to the 5 minus 3 to the 5b to the 5. Now let's work out what 2 to the 5 and minus 3 to the 5 are, and we'll multiply that by 252. So I just calculated 32 is 2 to the 5, minus 243 is 3 to the 5. Multiplied those together with the 252, and this is the big value that I got, and I've just popped in a to the 5, b to the 5. Now that's the coefficient, or that's the term with a to the 5, b to the 5, and this value here is the coefficient of that term. But the question said factored into primes, and that means we need to find our answer in terms of prime numbers. Now, we can't go from this answer here and work out prime numbers because it's going to take too long. So what I'm going to do is we are going to go from basics back here and see if we can get that in terms of primes. So remember what 10 choose 5 actually is. So remember what NCR is n factorial on n minus r factorial r factorial. So 10C5 is going to be 10 factorial on 10 minus 5 factorial, which is 5 factorial, 5 factorial. So that's what our 10C5 is. So the solution that we want to write is going to need to have that in it. So 10 factorial is 10 times 5 times, 10 times 9 times 8 times 7 times 6, all the way down to 2 times 1. And we've got 5 times 4 times 3 times 2 times 1, and we've got that twice. So what we actually have there is, one of these 5 to 4s is going to cancel out with that. So what we've got left of our 10C5 is 10 all the way down to 6, and on the bottom 5 down to 1. So let's now rewrite what we've got left here for 10C5 and include out 2a to the 5 and minus 3b to the 5. So I've just written that down here, including these parts out here, but we don't really need the coefficients. So I'm actually going to just remove the a and the b because, sorry, we only need the coefficients because that's all that the questions asked us to do. So we actually don't need those parts in there. So what we might do is split this minus 3 here up into minus 1 to the 5 and then 3 to the 5. That's where it gets a little bit tricky because it wanted us to work it out in primes. Let's see if we can make each of these numbers prime numbers. Remember, primes are numbers that can only be divided by 1 and themselves. So 10 could be 2 lots of 5. 9, we can write 9 as 3 squared, and 3 is a prime. 8, can we do anything with 8? Let's just go 2 times 4. The 7 we're going to leave as the 7. The 6 we're going to leave as 2 times 3. The 2 to the 5 stays as 2 to the 5. We've got, minus 1 to the 5. It's going to stay there, and we've got 3 to the 5. And the bottom line we've got 5 and 4 and 3 and 2 and 1. And now we're going to cancel things out. So everything on the top's multiplied, everything on the bottom is multiplied. So I can cross that 5 with that 5. That 4 can cross out with that 4. That 3 can cross with that 3. We'll go that 2 with that 2. And we've got the 1 that we don't need to deal with because it's just a 1. So what have we got left there? Now let's neaten up so that we don't have a bottom line anymore, but we've got 2's. We've got 1, 2, and 5 more over here. So we've got 7 lots of 2's. Now 3's, we've got 2 and we've got another 5. So we've got 7 lots of 3's. We've got 1 lot of 7. And we've got a minus 1 to the power of 5, which is still going to be minus 1. So I've basically just added powers to get down to here. And that's it. That's our answer. 2's a prime number, 3's a prime number, 7's a prime number, and 1 is a prime number, and there's a minus in there. And that's a product of primes. Well, that's a very different question. That'll get you thinking a little bit.